On Friday the 13th of April 2029, at 46 minutes past 9 in the evening Universal Time, an asteroid the length of 3 football pitches will pass over your head. It will pass about 31,600 kilometers above the surface of the Earth. That is roughly 5 times the radius of this planet and 1/10 of the way to the Moon. It is closer than the ring of geostationary satellites, the belt of communications and weather satellites that sits above the equator. The asteroid will pass beneath them. It will be visible to the naked eye. At its brightest, it reaches magnitude 3.1, a moving star, no telescope required, from rural and darker suburban skies. The approach will be visible from Europe, Africa, and Western Asia. Over about a day, it will cross 205 degrees of sky, from Centaurus to Perseus and then to Pisces. At closest approach, it will be moving 42 degrees per hour, fast enough that you can watch it move against the stars in real time with your own eyes. Its name is Apophis. It is 450 meters by 170 meters, elongated and bilobed, 2 lumps stuck together, possibly a contact binary. It will be the closest approach of an asteroid this size in recorded history. An object this big coming this close is estimated to happen about once every 800 years. And for 4 days in December 2004, some of the best informed people on Earth believed it might not miss. This is a story of how that number went to 2.7% and then to 0, and what it cost, and what it taught us. Apophis was discovered on the 19th of June 2004 at Kitt Peak National Observatory in Arizona by Roy Tucker, David Tholen, and Fabrizio Bernardi. It was a hard catch. The object was very far away and very close to the direction of the sun in the sky, which is the worst place to look for anything. It got the provisional designation 2004 MN. 4. It would not have a name for another year. Then, in December, it passed within about 14 million kilometers of Earth, and everyone got a much better look. What they saw eventually was a strange object. Radar images taken in 2012 and 13 showed an elongated body, bright for an asteroid, with a surface reflectivity of about 35%. Its composition probably matches a class of stony meteorite called LL chondrites. Its mass is put at about 40 billion kilograms, an estimate its own authors describe as good to within a factor of 3. And it does not rotate the way a planet rotates. Apophis is a tumbler. Its axis of rotation moves around inside the body itself. That axis takes about 263 hours to work its way around. The body precesses much faster, on average every 27.4 hours. The net effect is an object that appears to flip, roughly every 30.5 hours. It also spins backwards relative to its orbit, a retrograde rotator. Which matters, because the direction of spin determines which way sunlight pushes it. Better looks are supposed to make you calmer. This one did the opposite. NASA's Automatic Sentry System and NEO DICE, its European counterpart, both flagged a very close approach on the 13th of April 2029. Then, the impact probability started to climb. On the 27th of December 2004, it peaked at 2.7%, 1 in 37. Combined with its size, that put Apophis at level 4 on the Torino scale, the scale astronomers use to communicate impact hazard to the public. Level 4 remains the highest rating any object has ever received. Nothing before or since has been rated higher. On the Palermo scale, the technical version scientists use among themselves, it hit 1.10, an impact hazard more than 12 times the background level. Also a record. And then, later on the very same day, it went to 0. Before we get to how, a word about the name, because it is better than you think. The object was numbered 99,942 in June 2005, which made it eligible to be named by its discoverers. In July, they chose Apophis. Apophis is the Greek name of Apep, an enemy of the ancient Egyptian sun god Ra. He was the uncreator, an evil serpent who dwelt in eternal darkness and tried to swallow Ra during his nightly passage. He was held at bay by Set and Horus, the gods of storms and desert and of skies and plain, and Ra beheaded him, once in the form of a great cat in the shade of a temple tree. There was also a naming convention buried in it. The 2029 encounter will convert this object from an Aten-type asteroid to an Apollo type. Apollo asteroids are usually named after Greek deities, Atens after Egyptian ones. Apophis is the Greek name of an Egyptian god. It works either way. Two of the discoverers, David Tholen and Roy Tucker, are reportedly fans of the television series Stargate SG-1, in which one of the persistent villains is an alien named Apophis, a principal threat to civilization on Earth in the early seasons. Tholen has denied that the asteroid was named after the television character and says the connection is coincidental. The pronunciations even differ. The mythological creature takes the accent on the first syllable, the asteroid on the second. And in 2008, a software engineer named Dennis Moskowitz, who devised most of the dwarf planet symbols now in Unicode, proposed a symbol for it, based on ancient Egyptian depictions of Apep, with a star added in the style of 19th century asteroid symbols. To understand what happened that day, you have to understand something counterintuitive about impact probability. For a newly discovered asteroid, the number is supposed to rise first. When you first find an object, you do not know its orbit precisely. You know a region of possible orbits, an uncertainty region, usually a long, thin ellipse. At discovery, that region is enormous, and Earth sits somewhere inside it. Earth is a tiny target in a huge area, so the probability of hitting it is small. Every new observation shrinks the region, and if Earth stays inside the shrinking region, the probability goes up, not because the asteroid is more dangerous, but because you know more. That rise is not new evidence of danger. It is the sound of uncertainty collapsing. Eventually, the region shrinks past the Earth entirely, and the probability falls off a cliff to zero. Or it shrinks onto the Earth, and the probability climbs towards certainty. In December 2004, Apophis' uncertainty region had shrunk to about 83,000 kilometers across, and the Earth was still inside it. What killed the risk was not a new observation, it was an old one. Astronomers went back through images taken before the discovery and found Apophis sitting in plates from the 15th of March, 2004, 3 months before anyone knew it existed. That is called a precovery, prior recovery. Finding the object in the past, in data, nobody had reason to look at it. Extending the observation arc backwards by 3 months tightened the orbit enough to prove that on the 13th of April, 2029, Apophis will miss. The scare lasted 4 days. The instrument that ended it was a filing system, but ruling out 2029 did not rule out Apophis because of something called a gravitational keyhole. When Apophis passes this close, Earth's gravity will bend its path hard. It arrives at 6 kilometers per second, gets accelerated to 7.4 at closest approach, and leaves at 6 again. Exactly how much it bends depends on exactly where it passes. And there are narrow bands, keyholes, where the bend sets up a return collision years later. For Apophis, the keyhole that mattered was less than 1 kilometer wide. Pass through it in 2029, and you come back and hit the Earth exactly 7 years later on Easter Sunday, the 13th of April, 2036. A 1 kilometer target, 25 years out. That kept Apophis at Torino level 1 until August 2006, when the probability of threading it was found to be negligible. Radar observations at Goldstone in January 2013 effectively closed 2036 for good, which left 2068 and a different keyhole about 212 kilometers away from where Apophis was expected to pass. And to rule that one out, they had to measure something almost absurdly delicate, the push that sunlight gives an asteroid. It is called the Yarkovsky effect. A rotating body absorbs sunlight on its day side, carries the heat around as it turns, and radiates it from the evening side, and that radiation is a thrust. It is a tiny thrust. On Apophis, it shrinks the long axis of the orbit by about 170 meters a year. 170 meters a year on an object that travels hundreds of millions of kilometers a year. And that is the number that decided the question. In March 2020, David Tholen, one of the original discoverers, and David Farnakia measured that effect on Apophis for the first time. It shifted the predicted pass by 296 kilometers, enough to prove Apophis would miss the 2068 keyhole, which sat 212 kilometers away. On the 21st of February 2021, Apophis was removed from the Century Risk Table. No chance of impact for the next 100 years. And there is one more technique in that list worth describing because of who did it. It is called stellar occultation. You do not observe the asteroid. You observe a star, and wait for the asteroid to pass in front of it and blink it out for a fraction of a second. From the exact timing, at several places on the ground, you get the asteroid's size and position with extraordinary precision. In March and April 2021, 5 separate occultations by Apophis were successfully observed, the first time this was ever done for an asteroid so small. The previous record holder was more than 10 times its size. The campaign was messy in the way real observing is. The 7th of March worked from the United States. The 11th was predicted for Central Europe and lost to bad weather, 2 negative observations recorded from Greece. On the 22nd of March, larger than expected errors in the earlier data had sent most observers to the wrong place. It was seen by exactly one person, an amateur astronomer in the United States named Roger Venable. That single detection was enough to predict several more events that would otherwise have been unobservable, including one on the 4th of April, seen from New Mexico, again with Venable among the observers. 2 more, on the 10th and 11th of April. were caught from Japan and New Mexico by several observers each. Together, they refined the asteroid's size and its orbit. So, the record of this object includes radar dishes, spacecraft, national observatories, and one man in his garden who was in the right place when nobody else was. 17 years, from a 4-day panic to a clean bill of health, using precovery plates, radar, stellar occultations, and the pressure of sunlight. It is worth being precise about what the 2.7% meant, because the honest answer is serious and not the end of the world. An Apophis impact was estimated at about 1,200 megatons of kinetic energy. For comparison, the eruption of Krakatoa was about 200 megatons. The entire global nuclear arsenal is equivalent to about 1,460. And the Chicxulub impact, the one at the end of the Cretaceous, was around 100 million megatons. Apophis is not that. Apophis is not close to that. An Apophis impact would be extremely destructive across thousands of square kilometers and unlikely to have long-lasting global effects like an impact winter. On land, assuming a stony body into sedimentary rock, it would leave a crater about 5 kilometers across. In 2008, the B612 Foundation mapped where a 2036 impact would have landed to work out deflection strategies. They called it the path of risk. It was a corridor a few kilometers wide running across southern Russia, the North Pacific, between Nicaragua and Costa Rica, across northern Colombia and Venezuela, and out into the Atlantic. Simulations of an impact in the countries along that corridor produced casualty estimates in the millions. That corridor no longer exists. It was erased by better data. But it is worth remembering that it was drawn, because the drawing of it was the point. The Torino scale itself came out of this problem. It was created by Richard Binzel at MIT, presented to a United Nations conference in 1995, and adopted at a meeting in Torino, Italy in 1999. It runs from 0 to 10. 0 means negligible. 10 means certain collision, large enough for a global disaster. And in 2005, it was reworded because the press kept treating Level 1 objects as emergencies. Level 1 was renamed from events meriting careful monitoring to simply normal. Level 1 objects are discovered several times a year and usually last a few weeks before a longer observation arc erases them. That is the system working. Only 3 objects have ever been rated above 1. Apophis at 4 in 2004, 2004 VD17 at 2 in 2006, and in early 2025 an asteroid called 2024 YR4 reached level 3. Apophis is still the record. More than 20 years later, nothing has beaten it. And in 2022, we found out whether we could do anything at all. On the 26th of September 2022, a 610-kilogram NASA spacecraft called DART hit an asteroid moonlet named Dimorphos at 23,000 kilometers per hour, about 11 million kilometers from Earth. The success threshold was a change of 73 seconds in the moonlet's orbital period. The actual change was 32 minutes. Most of that came from recoil. The debris thrown off the impact pushed harder than the spacecraft itself did, an effect called momentum enhancement. It also very slightly changed the pair's orbit around the Sun, the first time human action measurably moved a celestial body. The catch is time. Deflection needs warning, typically years to decades. An expert testimony to the United States Congress in 2013 put the minimum preparation for an intercept mission at 5 years, which is why the surveys matter more than the rockets. You cannot deflect what you have not found, so 2029 is no longer a threat. It is an opportunity, and the world has already booked it. The OSIRIS-REx spacecraft, the one that brought a sample of asteroid Bennu back to Earth in 2023, had fuel left over. Apophis was the only asteroid it could reach for a long rendezvous rather than a flyby. Renamed OSIRIS Apex, it will arrive at Apophis in April 2029, days after the close approach, and study it for 18 months. It will do something clever, descend and fire its thrusters at the surface, blowing away the top layer to expose what is underneath. The European Space Agency has approved a mission called Ramses, Rapid Apophis Mission for Security and Safety, launching in 2028 and arriving in February 2029 before the flyby. Arriving before matters, because the flyby is going to change the asteroid, and they want the before picture. Earth's tidal forces are likely to alter its rotation axis. It will not come inside the Roche limit. It will not be pulled apart, but a partial resurfacing is possible, which would be extraordinary to watch, because it would change its spectral class, from a surface weathered by space to a fresh one, exposed by a gravitational encounter with our planet. Apophis will also change orbit. It arrives as an A10 asteroid, spending most of its time inside Earth's orbit. It leaves as an Apollo, spending most of its time outside it. One pass, one new class. It also meets the Moon, at about 89,600 kilometers from the lunar surface, 16 hours after it meets us. We have not been able to observe Apophis since 2021. Its orbit has kept it too near the Sun in our sky. The next look will come shortly before the flyby. So, here's where we are. An object was found. For 4 days, it was the most dangerous known thing in the solar system. Then, over 17 years, using archived photographs, radar, occultations of distant stars, and the measurable pressure of sunlight, it was proved harmless to a precision of a few kilometers, a quarter of a century in advance. And on Friday the 13th of April 2029, a substantial part of the human species will be able to walk outside, look up, and watch it go past, knowing exactly what it is and exactly where it is going. That is not a near miss. That is a species that learned to see in the dark.